All right, so this is the last of the videos to come from this particular set of lecture notes. I'm going to prove this last main theorem. Limits of functions in terms of sequences. Let U be a subset of R, let f from U to R be a function, let P be a limit point of view, and let L be an R. Then limit as x approaches P of f of x is equal to L. Nope, I want to highlight. This is true if and only if for every sequence xn of elements of U minus P, which satisfies that xn converges to P, it follows that f of xn converges to L. So this looks super similar to the same thing for continuity, with basically the exception being that the sequence is a sequence of elements of U minus P. So the proof will also feel pretty similar. Let's go through the proof. All right, here we are, the proof of theorem 3.2.3. So this is definitely something that if I were restricted to a 15-minute class period, I wouldn't do this at all. I would have you guys go through it. And in fact, I encourage you to pause this video right now. Try to suss out the proof from here. There might be some typos because I can't do anything correct. And come up with the proof. So let's do it. Let's let U be a subset of R, f from U to R be a function, let P be a limit point of view, and let L be an R. I need to prove that this is true if and only if that is true. And so an if and only if proof should have two directions. Let's do the forward direction first. Let's assume that the limit of x as x approaches P of f of x is L. I need to prove this. So I'll consider a sequence of elements of U minus P because I need to prove something is true for every sequence of elements of U minus P. I need to prove that if xn converges to P, then f of x converges to L. So let's assume that xn converges to P. I want to show f of xn converges to L. And this will actually be pretty easy. And I won't even do the walk off to the side because this is so very similar to what we just did. So I know that the limit as x approaches P of f of x is equal to L. I've considered any epsilon bigger than 0 because I need to if I want to show f of x of n converges to L. So what do we get out of that? Because the limit of f of x is equal to L, and this epsilon is bigger than 0, it follows that there exists a delta bigger than 0 such that for all x in U, if 0 is less than absolute value of x minus P is less than delta, then absolute value of f of x minus L is less than epsilon. Well, since delta is bigger than 0 and x sub n converges to P, there exists some big N such that for all little n bigger than big N, absolute value of x sub n minus P is less than delta. So this statement right here almost lines up exactly with the hypothesis in this if-then. The difference being that there's a 0 is less than there, there's no 0 is less than there. So let's consider any little n bigger than big N. Well then, by 3.8, we certainly have that xn minus P is less than delta. Now this xn is an element of U minus singleton P. So that means that xn is not equal to P. So that means that this difference is bigger than 0. So 0 is less than absolute value of xn minus P is less than delta. Now I'm set up to use 3.7, which is this. So I know that xn minus P is less than delta. So the if part of that if-then happens. So I get the then part of the if-then happens. So by 3.7, I then conclude that the absolute value of f of xn minus L is less than epsilon. Nice. So that does it, right? We started by considering any epsilon bigger than 0. So we know that something's true for every epsilon bigger than 0. We conjured up a choice of delta, but that was part of the proof, not part of the conclusion. What really matters is we came up with a choice of big N. We considered any little n bigger than big N and concluded that the absolute value of f of xn minus L is less than epsilon, so f of xn converges to L. There we go. So if we want to prove the Lavarche implication, we'll, just like the proof of the claim for continuity instead of limits, well, we'll prove the contraposition. We'll prove that if not f of x converges to L, then not for every sequence xn of elements of u minus p. If xn converges to p, then f of xn converges to L. Well, so let's follow the same logic. Let's assume not f of x, limit of x approaches p of f of x is equal to this. So f of x does not converge to L. And I'll need to prove that it is not true that for every sequence x sub n of elements of u minus p, if xn converges to p, then f of xn converges to L. I need to show that this is not true. Well, let's start by expanding out the assumption. So I'm assuming not limit as x approaches p of f of x is equal to L. Expanding this out using the definition of the limit, I see that we are assuming not the definition of the limit. Not for all epsilon bigger than 0, there exists a delta bigger than 0 such that for all x in u, if 0 is less than the absolute value of x minus p, then absolute value of f of x minus L is less than epsilon. Let's expand out that negation. It follows then that negate a universally quantified thing, we'll get an existential statement. We see that there exists an epsilon bigger than 0 such that for every delta bigger than 0, there exists an x in u. As a quick comment, different choices of delta result in different x's, right? X is allowed to depend on delta. It also depends on epsilon, but epsilon is a single constant. Such that negate an if-then, negate this if-then statement, we'll get and not. The hypothesis is true and the conclusion is false. 0 is less than absolute value of x minus p is less than delta, and absolute value of f of x minus L is bigger than or equal to epsilon. Now let's see what it is that we actually need to prove. So this is the thing that I need to prove. Negating that statement, there, it's still on screen. I see that the thing that we need to prove is that there exists a sequence, x sub n, of elements of u different from p, such that xn converges to p and f of xn does not converge. There's a negation of a converging thing. Does not converge to L. All right, well, there's what I need to prove. Let's try to cook it up. So we'll use this thing which is true, right? This assumption is definitely going to be needed in the proof. Otherwise, it wouldn't be an if-then. It would just be a thing that's true. So we're going to need to use that assumption. Let's consider this epsilon. That's some fixed constant. I know something is true for every delta bigger than 0, so I'll pick a sequence worth of them because I want to generate a sequence. So let's let delta be 1 over n. Maybe I'll even follow the same notation as before. Let's let delta n be 1 over n. I don't know why zooming works so poorly. The statement in 3.9, which I know is true, implies that there exists some xn. Let's decide where it lives. This is an xn in u, such that 0 is less than the absolute value of xn minus p is less than delta n. Well, let's see what we see. I want to generate a sequence. There's a sequence. It needs to be a sequence of elements of u minus p. It's definitely a sequence of elements of u. I need them to not be equal to p. But, well, by assumption, 0 is less than the absolute value of xn minus p. absolute value of xn minus p is bigger than 0 for every natural number n. So this xn is a sequence of elements of u different from p. On the other hand, xn minus p is less than this number delta n, and delta n converges to 0, so xn minus p converges to 0, so xn itself converges to p. Neat. Next, for each n, we have f of xn minus p in absolute value is bigger than this fixed number epsilon, which in turn is bigger than 0. So in particular, let's actually put a bit of an argument right here. If f of xn converges, then well, I have this statement right here that I can take the limit of. Then the absolute value of the limit of f of xn minus p, absolute value, is bigger than or equal to epsilon, is bigger than 0. So limit of f of xn is not equal to p if it even exists. And certainly if it doesn't exist, then it's not equal to p because it doesn't exist. So it follows then that f of xn does not converge to L. It might converge somewhere else, or it might diverge. I can't tell. Oh, neat. So I've just produced a sequence, xn of elements u minus p, such that xn converges to p, and f of xn does not converge to L. So we see that if limit as x approaches p of f of x is not equal to L, then what do we conclude? There exists a sequence xn of elements of u different from p such that xn converges to p and f of xn does not converge to L. Writing these as negative statements, well, this is already a negative statement, so there's a not equal to. So if it is not the case that the limit as x approaches p of f of x is equal to L, then it is not the case that for every sequence xn of elements of u minus singleton p, if xn converges to p, then f of xn converges to L. All right, so by the principle of contraposition, that's a not this implies not that. That's the same thing as saying that implies this. So the principle of contraposition now concludes that if for every sequence xn of elements of u minus singleton p, if xn converges to p, then f of xn converges to L. If that happens, then it follows that the limit as x approaches p of f of x is equal to L. So this means two things. If you want to show that a limit is equal to some number L, what you can do is consider any sequence of elements of the domain different from p, assume that that sequence of inputs converges to p, and then show that the sequence of outputs converges to L. And that's now a statement about sequences. We have lots of tools for studying sequences. Radical. So with that, I'll stop. That completes the discussion of limits in terms of sequences. And importantly, that means, in particular, the next lecture, whenever you want to prove something about, say, a continuous function, you can use the continuity to cook up a sequence of elements. And if you have a sequence of elements, you can use continuity to say something about the limit of f of x sub n. Awesome. So I'll stop here.